Good evening, children. Welcome to One Mark Solution. Please like, subscribe, and share to your friends. Now, let us move on to the case study of magnetic effects of electric current and magnetism, that is Unit 3. Now, let us move on to the case. We will see that, yes, that is Earth's magnetism. You know that Earth is having magnetism. Why Earth is having magnetism? How you know that? You just suspend a magnet or a magnetic needle. What you can see, always it is pointing towards north-south. Why it is always pointing toward north-south? Can be it is pointing towards south-north? No, no way. If you are keeping another magnet also, it will be going to the same. So that means the Earth is attracting this magnet. So sure we can say Earth is having magnetism. The magnetic field lines of Earth resemble that of a hypothetical magnetic dipole located at the center of the Earth. That means we can imagine that when magnetic dipole means a magnet is there, the Earth at the center of the Earth. The axis of the dipole does not coincide with the axis of rotation of the Earth, but is presently tilted by approximately 11.3 degree with respect to the later. You can see that the geographic north and south and the magnetic north and south is tilted. That means the axis also little bit tilted. That means by 11.3 degree, and this is called as declination, magnetic declination. That also you can see from the figure. And when we are drawing the magnetic field lines, we can draw from north to south. If the magnetic needle is perfectly balanced about a horizontal axis so that it can swing in a plane of magnetic meridian. What is this magnetic meridian? The vertical plane passing through the magnetic axis, we'll call it as magnetic meridian. The needle would make an angle with the horizontal, and this is known as the angle of dip, and we can call it as also known as inclination, magnetic inclination. One more word we have to study, that is horizontal component. And these three, magnetic declination, inclination, and horizontal component, we can together known as magnetic elements of the Earth. And that is very important also. And so many, cause of the Earth's magnetism are there. So we can go through the cause of the magnetism also there. First one, we can say gigantic magnet. Very, very early days, a gigantic magnet is buried in the Earth, that they have thought like that. But it is not, possible, isn't it? So another reason is so many charges in the atmosphere. If it is moving, we will get the current and we will get the magnetic field. And the next one, we can say that we will go for the outer core of the Earth. In the outer core, we can say the iron, nickel and all is there, and it is very very hot. The temperature will be very more. So what happens when temperature will be more? This one, that is the iron, nickel, will be in the molten state. So they will be circulating like this. If it is circulating, you know that they will be giving the magnetic field also. So many reasons are there for the Earth's magnetism. Now you can see a figure for the Earth's magnetism as well as the geographic meridian and the magnetic meridian below that. You can see just like a book, isn't it? And magnetic meridian and the geographic meridian makes an angle. That angle we'll call it as 11.3 degree. We'll take it as theta. And the other one, we can say the magnetic field. You can see AP, isn't it? You can see that AB, that is a total Earth's magnetic field. It can be divided. It can be resolved into two components. That is horizontal component and the vertical component. The total Earth's magnetic field will be making an angle theta with the horizontal. We will call it as magnetic inclination or dip. That is also very important. So three elements you have to study: magnetic declination, once again, magnetic inclination or dip, and the third one is horizontal component. Now let us move on to the questions. What is the angle of dip at the equator? At the equator, we know that only horizontal component will be there. What is the horizontal component? BH. What is BH? BH is equal to B cos delta. Delta or any letter we can use it. So if it is horizontal component B, H is equal to B cos delta. That is equal to B. So what happened? B and B cancel. Cos delta is equal to 1. If cos delta is equal to 1, what will be the value of delta? Delta will be 0, no doubt. So that is the answer. At the equator is 0, and at the pole also you have to study at, what is that, 90 degree. Don't get confused between these two. Now let us move to the second question. At the poles, yes, that is a question here. At the poles, the dip needle will be, is it horizontal, is it vertical, or stayed 45 degree with the horizontal, does not remain steady in any fixed position? Sure, it will be in the vertical position. That means in the pole. So it will be in the vertical position. So which is the answer? We can say B. And in equator it will be horizontal, and it in the poles we can say it will be vertical. That is why the value of dip is 90 degree. Now let us move on to the next one, third question. The angle of dip where the vertical component of the Earth's magnetic field is equal to the horizontal component of the Earth's magnetic field will be, we have to find the angle. So see that I have written, what is it? BV is equal to BH. How you know that BV is equal to BH? It is written there in the question. BV is the vertical component, BH is the horizontal component. So we have equating these two. What is BV? B sine delta. What is BH? B cos delta. So we can cancel B and B. What is remaining there? Cos delta, we can take the letters. So it will be sine delta by cos delta. What is it? That is tan delta. So we will get tan delta is equal to 1. Then what will be delta? If tan delta is equal to 1, delta will be 45 degree. So what is the answer here? We can go through the answer 0, 45, 60, 90. So the answer will be 45 degree. B. The option B. Now let us move on to the fourth one. Which of the following independent quantities is not used to specify the Earth's magnetic field? We'll go through the answers. Magnetic declination, of course, we are using it. Angle of dip, yes. Horizontal component, these three are the magnetic elements. Then we'll go for the fourth one, vertical component, we are not using it. What are the magnetic elements actually? The magnetic elements are the physical quantities which explains Earth's magnetic field completely. What do you mean by completely? Completely means in magnitude and its direction. So what is the answer here? The answer will be D. Fourth one, D. Yes, that is the correct answer. Now let us move on to the fifth question. The vertical component of the Earth's magnetic field at the place is root 3 times the horizontal component. The value of dip at this place, we have to find it out. So here we are just finding the value, that is BV. BV is vertical component, BH is the horizontal component. So BV is equal to root 3 into BH. So how will you find the angle? We can take BH to this side. BV by BH is equal to root 3. What is BV? B sine delta. And BH is cos delta. Sine delta by cos delta, it will be root 3. And you know that sine delta by cos delta is tan delta. So what will be the answer? When we can say tan delta is equal to root 3, when will be the angle? Is 60 degree. Very good. So the answer will be A, 60 degree. So please go through all the theory. That means the concept clear and the equations clear. So you can gain, or you will get, surely you will get the marks on the Earth's magnetism. Please study Earth's magnetism. Why? Because in the magnetism and matter, the fifth chapter, so many portions are deleted. So please concentrate what the topics which is very important. Thank you for watching 1 mark solution.